mobile phone, preference of choice of online mode of a teaching. So this is also an example of a ordinal data. Whatever the data you are collecting based on a preference, these are said to be ordinal data. Now, if the difference between two categories known and equal in the ordinal data, then such data is said to be interval data. And interval data is a specific example of a quantitative data. It is a specific kind of a quantitative data. For example, you have measured the information on a 5-point scaling. 1 means the worst, 5 means the very good, 3 means the neutral. So you can see that the difference between the perception of 1 and 2 is remained the same between 2 and 3, and it remained the same between 3 and 4 and 4 and 5. So what it suggests that the difference between two categories is known and equal. So it is not an ordinal score, it is now interval score. And interval score is the part of a quantitative data. And that is how whenever we have measured the data on a 5-point scaling, we say that we can apply all the quantitative techniques. Now, but there is a problem of a quantitative or the interval scale is 0 is arbitrary. For example, if I have taken your mock test, in a one mock test, your score is 0 out of 10. So can you say that your IQ is 0?
No.
If I will take the another mock test and you will get the 10 out of 10. So can you say your IQ level is 100?
No.
So marks cannot measure your IQ level. That means 0 is fixed. Even though you got the 0 out of 10, still your IQ level is not fixed. So that means 0 is not fixed. 0 is arbitrary. So what it means, when 0 is arbitrary, you can not use the interval scale. One has to define the another scale, and it is called a ratio scale. So where ratio is a scale where it satisfies all the properties of nominal, ordinal, as well as the interval scale, but 0 is fixed. And that is how all the financial ratios are the example of a ratio scale. 0 means 0. It is fixed means fixed. Your weight is 0 means 0 with respect to Earth. Then don't tell, sir, if we go to the moon, then our weight is different. So whatever the weight you have defined, 0 weight, 0 kilogram means it is a 0. You can measure with any weighing machine. The weight 0 means 0. So that means it is the classical example of a ratio scale. Why there is a need of study of nominal, ordinal, interval and ratio scale? Why there is a need of study of a qualitative data and quantitative data? The reason is that statistical techniques have been developed based on the measurement of a scale. If your data is a nominal, you cannot use the technique like regression analysis, factor analysis, etc. If your data is of a quantitative, you cannot use the analysis of variance, because in ANOVA you have the approach. If your data is of a quantitative, you cannot use the chi-square test unless and until you convert the quantitative data into the qualitative data by making the some categories. That we usually did in the second year of B.Sc based on the which method, where we have converted raw data into the group data. So that rule is a Sturge rule. On that, we have converted the quantitative data into the qualitative. Then you can use it. So what I mean to tell you that whenever you have encounter with any data, you have to first study the nature of the data. You have to study the nature of the variable, whether it is a qualitative or whether it is a quantitative. Without looking the nature of the data, don't jump directly into the modeling. So here, that is what the difference between the second semester and third semester is over here. In second semester, we have considered the concept of a modeling where y is a one variable, x is another variable. We call them in the second semester y is a dependent variable and x is a independent variable. Okay, but here we have considered in the second semester y and x both are quantitative in nature. For example, if you talk about the weight of the individual, so it is a function of the height. Okay, yeah, amount of a food, weight of a fish gain, it is the amount of a food, how much food you are giving to them and what kind of the weight gain you will observe in the fish. So what I mean to tell you that in second semester we have considered the model where y and x both are quantitative in nature. But when we come to the third semester, we say that suppose y is coming from exponential family of distribution. You have studied in the second semester the exponential family of distribution. Exponential family contains several distributions. Several distributions are the member of exponential family. What are the distribution? So you can say that by Bernoulli distribution is a member of exponential family of distribution, binomial distribution, Poisson distribution, then gamma distribution, exponential distribution. These are all the members of a exponential family of distribution. In second semester, we have developed the regression model where we say that the relation between y and x is linear, y is a dependent variable, x is independent variable, and there is a some random quantity. It is called the epsilon. So what is the epsilon? The epsilon having a specific distribution. And what is the distribution we have considered? It has the normal distribution with mean 0 and variance sigma square. So we have only considered the normal distribution. But normal distribution is a member of exponential family. So instead of developing the model that epsilon having a normal distribution, we say that epsilon having a member of family of exponential family of distribution. So if epsilon having a normal, so we know that due to the linearity property, y having also a normal distribution. So we say that y follows the normal distribution in the second semester. But in this semester, we say that y follows the exponential family of distribution. So rather than study as an individual class, we will generalize the classical linear models. And that is how the name of this topic is a generalized linear model. So we are generalizing the classical linear models on the line of the assumption of a classical linear model. So we will retain all the assumption of classical linear models, but we will generalize this class. So it is said to be a generalized linear models. So it means that when your response is binary, linear models does not help you. Regression model does not help you to develop a models. So which model is possible? So it is saying that if the response is binary, one can go for the either binary logistic regression or discriminant analysis. So when you say that response is binary, so with distribution having a binary response, with distribution having a binary response,
Logistic
Bernoulli.
regression.
So Bernoulli distribution having a binary response. And if you make some transformation, then it will transform into the logistic model. So that we will see when we come to that part, how the name logistic regression is given, because its cumulative function is of a logistic distribution function. So what I mean to tell you, if the response is binary, it has a Bernoulli distribution. If response is a multinomial, then it has a multinomial distribution. If response is a count, then it has a Poisson distribution. So if response is a Poisson, we have a Poisson regression model is there. If response is a multinomial, then we have a multinomial logistic regression model is there. If your response is a gamma, then we have a generalized linear models having the gamma response is there. It is also known as a constant CV model. So there are various approach. We will start one by one. If response having a binary, there is a one unit. If response having a count, then there is a 1 unit. If response having a gamma, then there is a 1 unit. So entire generalized linear models is divided into the 5 units. In the first unit, we will discuss about what is the generalized linear models, what are the basic steps of conducting the fitting of a generalized linear models, what are the basic assumption of a generalized linear models, to fit generalized linear models, what you require. So that we will see one by one. Again, I will go back to my linear model parts, because yesterday we were discussing about the linear model parts and regression analysis. So in linear models, as I say that we have the model y is equal to x beta plus epsilon. Our basic idea is to estimate the parameters of a linear models, and we have applied the concept of theory of least squares to obtain the estimate of the parameters. So how the ordinary theory of least square is help? It is simply saying that you have to minimize the residual sum of squares. So how will you minimize the residual sum of squares? So first that you have to write down the residuals. So residuals is nothing but it is the difference between the observed and estimated or predicted value. Just write down the residuals sum of square, take the derivative with respect to parameter beta. You have a set of normal equation, and normal equation you got it x dash y is equal to x dash x beta. Okay. Now, if the rank of x dash x is not full rank, then we will not get the unique estimate of the parameter beta. If it is a full rank, then naturally you can say that x dash x inverse is invertible, so that beta cap equal to x dash x inverse x dash y, and that you will get the unique estimate. And if because epsilon having a normal, that is y having a normal, and therefore beta cap having also a normal, because beta cap is a linear function of y. And then you can find out its mean and variance. But suppose it is not estimable, or suppose the rank of x dash x is not full rank, then the model y is equal to x beta plus epsilon is known as a non-full rank model, and you cannot obtain the unique estimate of the parameters because inverse is not exist, and that is how you will develop the generalized inverse, and that you write beta cap equal to x dash x bar x dash y, or you can say that s bar q, where s equal to x dash x. This is what we have studied in the second semester. So are we in that position to obtain unique estimate of the parameters which are estimable? This is one idea. Or if it is not possible, are we in that position to obtain some linear function of parameters which are uniquely estimable? So let us say the linear parametric function is lambda dash beta. So first, whether it is estimable or not, you have seen the various condition of estimability, lambda dash equal to u dash x and lambda dash equal to lambda dash h. And once it is estimable, you will go for finding out the whatever estimate of the beta cap you are getting, that is how you are substituting into the lambda dash beta. Your estimate of lambda dash beta is a lambda dash beta cap. So you will have some estimate of the parameters, which is unbiased for lambda dash beta. Then you can find out its mean and variance, because beta cap having a normal distribution, then lambda beta cap having also a normal, and then its mean is lambda dash beta and variance is lambda dash s bar lambda dash, something like that. So whether whatever the estimate of parameters you are getting, whether it is unique or not, how will you check? So of course the Gauss and Markov has given the theorem to obtain the best linear unbiased estimators, which is uniquely estimable, and you will find out the blue, and then you find out its variance, blue variance of the blue, covariance matrix of the blue, and something like that. Then you can find out because you wish to test lambda beta equal to t, that is the test of hypothesis. So when we go for the testing of hypothesis, we require the distributional assumption of epsilon, and we assume it has the normal. So because epsilon having a normal, residual having also a normal, so residual square having a chi-square distribution, and lambda dash beta cap having a multivariate normal distribution, if we estimate the m parametric function which are estimable, And then it has we have calculated the regression sum of square, and regression sum of square is nothing but beta dash cap x dash y, and we found out that it has also a chi-square distribution, and then ratio of two independent chi-square divided by corresponding it has the F distribution. Then we will all entirely do the testing procedure. So this is all about the linear models. But now the same thing you can go for the regression models. Procedure remain the same. Suppose when you come to the regression model, we say that all x's are independently distributed. Y is a function of x, which are linear in parameters. Epsilon is independently distributed with x. Epsilon is independently distributed with y. So these are the basic assumptions. And if only a single regression, then we call them as a simple linear regression. If there are more than one regressions, then we say it is a problem of a multiple linear regressions. Why it is a linear? Because the relation between y and x is linear in nature. Okay. Now, here we have assumption that all x are independently distributed. All x are independently distributed. But suppose that assumption is violated. Then what we do? Suppose that assumption is violated. What we do? So when we say that assumption is violated, it means that some of the regressions are correlated with each other. Because when we fit any regression models, what we do? We'll try to verify the basic assumption. What the assumption? We develop the models. Actually, we are trying to see that the y having a normal distribution or not. We make the histogram, whether it is a symmetrically distributed or not. We make a box plot, and based on the box plot, we can see that is there any outlier in the data or not, whether it is a normally distributed or not. And we will find out the 5-point summaries like mean, median, mode. We find out the skewness and kurtosis. Based on that, we can take the decision. We can make the stem and leaf plot. Okay. One can perform the Kolmogorov-Mindro test for the normality of the data. Likewise, we will verify this whole assumption. Then we draw the scatter plot and try to see that what is the relation between y and x, whether it is a linear or not. If it is a linear, we will calculate the correlation value. If the correlation is significant, we'll go for the linear regression analysis. This is the basic procedure of performing the regression analysis. And before going to that, we will try to see which okay, before going to that, what we try to see? We try to see that the relation between y and x is logically true or not. Suppose if I am saying that there is amount of the rainfall at the Gujarat and the heavy production or the amount of the production is taken at the Maharashtra. Both are the numbers. Rainfall of the Gujarat and the production of a yield in the Maharashtra. Is there any logical connection between them? No. And therefore, we cannot develop the regression model. So before applying any modeling, we have to see that the logical relationship exists between the y and x or not. Since it is reasonable, but we have to see that what is y and x. If you are talking about the Maharashtra, then I have required the data of amount of rainfall of the Maharashtra, not of the Gujarat. Okay. Then you develop a models, like you are writing the simple models, and then you obtain the estimate of the parameters using the least square method. And after estimating the parameters of least square method, you will proceed. But here the thing is that because we have a more than one regressions, and that regressions are correlated. And if that regressions are correlated, we call them as a problem of a multicollinearity. If there is a correlation exists among the variables, we will not able to obtain the unique estimate of the parameters which are estimable. So then again we'll have to go back to the general linear models. We are not interested in the general linear model. We are interested to see that what is the impact of a specific variable on the y. That means we are trying to obtain the estimate of the partial regression coefficient. So we cannot directly apply the model. And if we do the modeling, what will happen? Either it will give the overestimate or underestimate. For example, if we develop the models and we say that there is a heavy amount of the sugarcane production in the Maharashtra, without looking any assumption we have developed, because we know the R, we have supplied the data and we say that, oh, there is a heavy amount of the sugar cane production at the Maharashtra region. So when there is a heavy production, what happened? Sugar industry came into the picture, government came into the picture, what should be the minimum support price? Many things are related with that. So as a statistician, we have to keep our ethics in mind. Whenever we are developing the models, we have to see that whether whatever the models we are developing, are we having a basic fundamentals with us? Are we maintaining the foundation before developing the models? Okay. Saurabh, please mute your mic. Okay. So what I mean to tell you that if there is, you say that we know R sir language and we have the data of the amount of the rainfall and the sugar cane production, and it is saying that there is a very good models, like some of the students are working in the agroeconomics project, and if they directly give the models without looking the assumption, and it is saying that there is a heavy amount of the sugar cane production, there are several planning has to be made by the government. And then you have developed the import-export policy because we have a heavy production. So what we do, we have a heavy production of a sugar, and when we have a heavy production of sugar, what we do, we will export the sugar to the, let us say, the UAE, because they are selling us a petrol, so let us give them to the sugar. And once the export-import policy is decided, we have to sell them anyhow, whether it is available to you or not. And later on, when the production came, you realize that actually we have overestimated the model, because before production you have to make all the planning, and you do not have a much quantity of the sugars, but because of there is a contract between the two countries, you have to simply supply that sugar to that country, and here there is a heavy price of the sugar, and then there is a problem with the government. This government could not able to control the sugar, and how can we as a common man drink a tea, because in the tea the sugar is very important role, and सबकी सुबह चाय से होती है, गवर्नमेंट की हालत बिगड़ जाती है, ठीक है. So who is responsible? Is the government is responsible? No. Who has supplied the data, who has developed the models, these people are the responsible. And that is how the Indian statistical system is entirely functioning on that. They are collecting the data at the various level, and they are collecting information, and just they are discriminating information. And then as an econometrician, as a statistician, it is our duty to give the appropriate policy so that the person who is outside in the government and inside in the government, they should be benefited with the some policy. Okay, so this is the role of a statistician. So before developing any models, we have to see the basic assumption. Now, as I say that because of the multicollinearity is present, that you have not studied the multicollinearity and you have directly developed the models, this is the one scenario. It may possible, it may underestimate the model. आप बोलेंगे कि there will be a not heavy production of a sugar cane. So what we do? We will have to import the sugar from the various country. So we know that we are importing the sugars from the mainly Pakistan, because Pakistan is also considered to be a heavy sugar hub, manufacturing hub. And now you have started importing and you realize that there is a heavy sugar production over here. Then again there is a problem. Okay, so whenever we develop the models, we have to see that basic assumptions. when we develop the building, we have to see that whether the foundation is correct or not. If the foundation is not made appropriately, what will happen? The building will collapse in a couple of years. So similarly, here we have to be very careful while developing the model. So how will you, so as it is identified that multicollinearity is a problem. What is the multicollinearity? When there is a relation among the regressors are there, then we say that there is a collinearity is present. If there are two variables and if they have the relation, which variable? Independent variable, regressors. So if there is a correlation among the two regressors, we say that there is a collinearity problem. But if there are several variables are correlated with each other, then we say that there is a problem of a multicollinearity. So multicollinearity is a problem. We know that. So we require some remedial measures. So before going to the remedial measures, before going to the treatment to the multicollinearity, we have to understand what is the multicollinearity, how to detect it. So how to detect the multicollinearity? We have seen the several things. If we develop the models and if there is a high pairwise correlation exists among the regressors, what we say that there is a high multicollinearity present. But we say that the high R squared, high pairwise correlation, it is a sufficient condition, not the necessary condition. Okay, sorry, it is a necessary condition, not the sufficient condition. Then we have seen that the high pairwise correlation, but few significant T ratios. So that some of the points we have seen in the second semester. Then we can calculate the VIF value, variance inflation factors. We can calculate the auxiliary regressions. Higher the RI square, that means ith auxiliary regressions value, we say that there is a presence of a multicollinearity. Higher the VIF, there is a presence of a multicollinearity. Lower the tolerance, because tolerance is the inverse of the VIF. So we can say that there is a multicollinearity is present. So these are the several symptoms of addition of a multicollinearity. Now how to remove it? So people are saying that several authors have given the different way. These are all rules of thumb. किसी एक को ध्यान में रख के नहीं चलना है. We have to see the various things. What it is saying that if you have the previous information that which variables are correlated with each other, drop the variable. So dropping of the variable, and when you drop the variable, what happens? You will allow the bias. So that means dropping of the variables and allowing the bias. So this is not the good sign of tackling the multicollinearity. Then somebody said that multicollinearity is not the problem of the population, it is a problem of a sample. So can we take another sample and then identify whether the multicollinearity is present in your data or not? But to take a sample, another sample, it is difficult because it is very costly. You know that you ask the Dipesh and the Dauda, see how it is difficult to collect the data and how much cost is associated, because they are associated with some agroeconomic project. So that means to collection of the data is not so easy. Okay, so that is not viable. Then somebody said that because the multicollinearity is a problem of a sample, not of a population, can we take some more observation and add the data? So adding of the data and solve the problem. Somebody say that can we club the data of a time series and cross-sectional? Time series data means a data which is collected order of time, and cross-sectional means at the same point in time you are collecting information at several places, and if you club it, perhaps it may handle the problem of multicollinearity. These are all rules of thumbs. So somebody said that no, we do not have any idea, we don't want to check this. Can you suggest some mathematical measure? Yes, there are two mathematical approaches to tackle the problem of multicollinearity. What is that? This is principal component regression analysis, PCR. So what we do, we will apply the principal component transformation on the dependent variable. Which are dependent variable? X. So all independent variables are correlated with each other. So we will apply the concept of a principal component analysis. Just apply the transformation, and after applying the transformation, what happens? This all dependent variables is converted into the independent variable. So how principal component analysis works? It will works on the method of a dimension reduction. First, you find out the first principal component. First principal component explain the highest variation. Then you will extract the second principal component, which explain the second highest variation. The component should be explained in extracted in such a way that the second principal component is independent of the first principal component. Likewise, you have to extract the third. The third is independent with the first as well as the second. So what I mean to tell you, you have to proceed extraction of a component in a same manner. And at the end of the day, you will extract the component. How many components can be extracted? It may be extracted that much of the variables is enter in your model. That means independent variable. If there are k independent variables, maximum k component can be extracted. But how many components you have to select? Whether should I select the 2 component, 3 component, 4 components? Then there is a method. If 3 component explain the 90% of information about the containing the data, then why should I unnecessarily add more components to get more information? 90% is sufficient. So I will only select 3 components. Somebody say that we will apply the concept of the scree plot. So scree plot is giving the idea of selection of a component. Somebody said that no, I will just apply the concept of a eigenvalues, that is the component value eigenvalues which is exceed the 1. So now the thing is that how to extract this component. So we know that in the first semester you have studied in the matrix algebra how to calculate the eigenvalues and eigenvectors. And for applied statistics, you must have studied in the second year B.Sc in a matrix, linear algebra and vector algebra, that how to calculate eigenvalues and eigenvectors. So eigenvalues in our setup, it is said to be a principal component. It is a variance of the first principal component. Eigenvector is nothing but the weight of each variable in the component. So once you identify the number of components, what you do? You regress your component on the y instead of x. Now you are regressing transforming variable onto the y. And because we are applying the concept of the regression analysis, it is said to be a principal component regression analysis. I think somebody's mic is on. Varsha, please mute the mic. Okay. So this is the concept of a principal component regression analysis. This is the mathematical measure and it will give you the output. Now another approach is that we will have suppose we don't want to restrict ourselves or rigid ourselves with the best linear unbiased estimator. We say that a linear unbiased estimator, that means we say that an estimator which is unbiased and having the smallest variance. So suppose if we drop the property of the unbiasedness and we try to see that which having the smallest variance. So when you say that the estimator is a bias, you will look for the mean square error rather than the variance. So you will go for the M.Sc instead of the variance. So what you will do? You will try to drop the property of the unbiasedness and develop some bias estimator. So we know that our normal equation is x dash y is equal to x dash x beta cap. It is giving the same, either you apply the linear models regression analysis. Okay. So what we do, we will allow the small bias because x dash x is not invertible. So we will write x dash x is equal, x dash y is equal to x dash x plus ki or nu I bracket over beta cap. And now earlier x dash x was not invertible, but now we have a x dash x plus nu I is a invertible. And then you can find out the beta cap. So this beta cap is equal to x dash x plus nu I inverse x dash y is said to be a Ridge estimator because you have allowed the bias, and it is a linear combination of the OLS estimator. That question I have asked in the mock test as well. And then you will calculate the M.Sc, and it is showing that the M.Sc is less than the variance of the best linear unbiased estimator. So this way you can find out the Ridge estimator. Now the question is that what should be the amount of the bias you should allow in your data or in your estimator. So that bias can be assessed based on the Ridge trace. Where the Ridge trace is minimum, that value of the bias coefficient you have to select. So you all have that materials, you have already studied, so you know that what are the formulas and how to calculate it. So you have to find out, you have to just calculate the trace of the estimator or the trace of M.Sc and subject to the different value of k, and just make a plot where you can see that the trace value is lower, that unbiased estimator you have to, that unbiased coefficient, bias coefficient you have to select, and that it will give you the Ridge estimator. So these are the different way to tackling the problem of a multicollinearity. Once your model is developed, you will go for the goodness of fit criterion. Yesterday we were talking about the R square, adjusted R square, AIC, BIC, and Mellowcity statistics. R square and adjusted R square are the criteria when you have a nested model kind of consideration. Okay, but if you are talking about non-nested model, R square adjusted R square does not help you. You have to go for the AIC or BIC. We know that higher R square, higher adjusted R square, better model. We know that lower AIC, lower BIC, better the model. And in a Mellowcity statistics, this criteria can work on a nested kind of a model comparison. And it is saying that the lower CP, and especially CP equal to P line, we say that that particular combination is suitable for the model development. Here P is a number of regressions allowed in your model. Once this all goodness of fit criteria has been passed, then you will try to see that is there any outlier present in your data or not? Is there any heteroscedasticity is present in your data or not? And suppose if there is a heteroscedasticity is present in your data, how will you check? So you can make the plot of residual versus predicted value. And if you get the certain patterns, we have seen the various patterns like the open funnel, like the blow funnel. So various patterns are there. And if you get such kind of a pattern, we say that there is a heteroscedasticity is present in the model. And when there is a heteroscedasticity present in the model, you cannot apply the ordinary least square method because it is not the suitable. So which method you have to apply? You have to apply the generalized least square estimation method. We call them as a Aitken estimation. We can sometimes call them as a weighted least square method, likewise. So you can apply these methods and then you can obtain the estimate of the parameters. It means residuals play a very vital role to detect the outlier in your data, to detect the influential point in your data, to detect is there any leverage point is available in your data, or especially you wish to see that heteroscedasticity is present in your data or not. So there are various kind of a scaling of residuals are there. What are the residuals? It is a ordinary residuals, standardized residuals, then studentized residuals, then press residuals, and R student residuals. So in yesterday lecture we have discussed about that and why we have to go for this. Why from ordinary to standardized residuals we have to go? Because to detect the outlier, we say that if we have seen 3 sigma limit in the control chart. So here we say that if it is a standardized residuals, the standard deviation value is 3. That means plus or minus 3. If any one of the point is outside this limit, we say that the point is an outlier. In our control chart, we say that that point is said to be out of control, or production is said to be out of control. So we are using that criteria, but here we say that the variance of epsilon square is sigma square, and then we have just divided by sigma square. But we are not calculating EI and their variance. We are calculating the variance of residuals. And when you say that variance of residuals, it means that variance of EI is not sigma square, it is sigma square into 1 minus HII. So what is HII? HII is nothing but the ith leverage point. And how will you find out the leverage point? How will you find out the leverage point? So how will you find out? The leverage point is a point which is far away from the centroid point of a x space. Means whatever the data of x variables are given to you, you find out their centroid and try to see that how the point is far away from this center. So if there are so many points are there, so with such kind of the point is said to be a leverage point. And again, leverage point method is there to measure. You calculate such HII and you find out whether this point is a leverage point or not, based on comparison of HI is greater than 2 times P bar, something like that. Okay. Now, whether this leverage point is really influential point or not, how will you go for it? So you will calculate the Cook distance, and based on the Cook distance, you can decide if the Cook distance value is greater than 1, we say that the ith point is a influential point. If the point is a leverage, then we do not have a problem in the regression analysis. Why? Because leverage point does not destroy the property of Euler's estimator, or you can say that it does not affect the regression coefficient as well as the mean square error. So we can develop a models with the leverage point. But if it is an influential point, then we have to see that whether this influential point is a data entry error or not. Sometimes what happens, if you are typing 10, instead of 10, you may type 100. Okay, so we have to cross verify whether it is a correct data or not. And if it is a something higher, then we have to put from our model, and then we have to develop the regression model. And then we have a separate task is given to that influential point. Why this point is influential? What happened at that time so that we get the higher? Suppose if it is a productivity is higher, then so what happened at that time of X so that my Y value is high? So I have to identify that combination and then try to perform some more experiment at that combination. Are you getting the higher value? If it is yes, then sometimes that influential point is very important. Okay, you just remove, but you have a separate inspection of that. And then you will perform once you have all residuals are there, press residuals we have discussed yesterday, that you have to, how to find out the press residuals. Press residuals is also known as the deleted residuals. That means every time you have to remove the ith observation, and then you have to develop the models. And then whatever the predicted value you have, that you subtract from the observed, it is giving the deleted residuals. And you can calculate the press statistics. Higher the R square, higher the R square press, we say that the better the model. So there is another criterion of press statistics. Even your model is good or not, that also you can identify based on the lack of fit test. So you have also studied the lack of fit test in the second semester. So lack of fit test is a kind of a test whether when you develop the models from linear to quadratic, and though it is a polynomial models, from linear to you go for the second order polynomial, third order polynomial, whether the upgradation is allowable or not. So how will you identify? So you have to perform the lack of fit test. If you start with a linear, and if the lack of fit test turns out to be significant, what it suggests that the linear model is not suitable, some higher order term you can add. And still if lack of fit test significant, then we can add further. Especially when we apply the concept of design of experiment, or especially in a response surface modeling, we use this concept of a lack of fit test. Okay. Now, one more thing is, so how will you calculate the lack of fit test? So lack of fit test can be calculated based on the split off of the pure error. So pure error, sorry, the error sum of square, SSE, is divided into the two parts. One is a sum of square due to pure error and sum of square due to lack of fit. And then you have to perform the ANOVA, and if sum of mean square due to lack of fit divided by the mean square due to pure error, it turns out to be significant, then we say that the lack of weight turns out to be significant, and that means we require to improve our model. So these are the all the aspect which we have studied in the second semester. That all aspect is again continue in the third semester, even in the fourth semester. So whenever you do the modeling, these all are very important. It is not like that ki I have studied in the second semester, my role is over, forget about it. No. When you come to the third semester, after passing examination, then naturally whatever the things we will discuss, I say that we have already studied in the second semester. This just carry forward from there. We will not discuss again. So still your examination is not completed. Read carefully. Overall, we have revised your second semester entire syllabus in a one lecture. Just giving the brief idea and the chronological order of a development. I have this recording facility is there, and I will see that record. And if the record is appropriate, then I will share you that record simultaneously. Okay. Any questions so far? So tomorrow we will we will start the first session of generalized linear models. Why generalized linear models, and then what are the different steps are required, that we will discuss, and I will share you the calendar of a 1 week or the 2 weeks, so that you do not require I do not require to send every time the link to you. Okay. Any questions so far about the linear models and regression analysis? So thank you very much. And I think you have another lecture at the 12:30 of design of experiment.
Yes.
So take a few minutes of break, because it's very difficult to connect continuously on the online lecture. Thank you very much. See you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.